Okay, so we will start the afternoon session of today with Yupeng Wang that will discuss about analytic better on that and a complete story, let's say. Thank you, Yupeng.
Okay, good afternoon, everybody. So firstly, I'd like to thank Sam for his kind invitation. Really enjoy the city, the scenery, and the climate. So today I'll talk about the off-diagonal beta answers. So I'll just give an analytical version of the beta answers. So, okay. So this one. Okay. So, at the start, I'll give a brief review why we study the problem, and then I'll give you an introduction about the off-diagonal beta answers, how to get the spectrum, and how to calculate the physical quantities in thermodynamic limit, and also how to retrieve, how to get the eigenstate from the spectrum. And I'll show you two examples. One is the exact quantization in a topological space without U1 symmetry, and also the second example is the spectrum of the spin chain with arbitrary non-diagonal boundary conditions. Finally, I'll give you the concluding remarks. Okay, so as we know, so an important issue in physics is the boundaries. But for the integrable models, there are two typical boundaries. One is in the compact space, and maybe in this space there is some knot. That means some topological structure, not a simple periodic boundary, but with some topological structure. And the second one is open boundaries, and the boundaries may be non-diagonal. So those boundary conditions may destroy the U1 symmetry, and which makes the traditional beta answers procedure very difficult. So, okay, so now let's turn to the off-diagonal beta answers. So just consider a simple R matrix. This R matrix possesses some intrinsic properties. One is the initial condition, and that means at the zero spectral parameter is proportional to permutation operator. And the second is a unitary condition, which means okay. And the third one is a crossing relation. So these three basic properties just determines almost all the properties of the transfer matrix we define as below. But here we just introduce some inhomogeneous parameters on each side. It's just the auxiliary, and which makes the process very simple and clear. Okay, so from the monodromy matrix, we can define the transfer matrix that trees over the auxiliary space 0. And from the Yang-Baxter equation, we can get the transfer matrices. No, this one. This one's better. Yeah. Okay, so we can get a commuting transfer matrices with different spectral parameters. And so from this basic properties, we can get, so from the definition of the transfer matrix, we get here, so the JS R matrix is at this, at this special point, the JS R matrix is permutation operator. So we can move this permutation operator throw out all the run, and we can then trace the auxiliary space. We get this expression. So just a product. Okay. And from this crossing relations, we can get the transfer matrix at different points, see j minus 1. So with this relation, we get the j's. So then we can inverse the order of the product, but the j's, the g, where's the j's? Okay, the j's R matrix becomes the permutation operator again, and then we can trace out. So we can see here the order of the product is inversed, and then we take the product of t theta j times t theta j minus eta. So with this unitary condition, so these two elements of product is scalar, is identity. So we can, see here, this one times this one, get a scalar, and then we get a scalar function. This is the identity. This at n different points, we get identities. Notice that Tu, the transfer matrix above the spectral parameter, is a degree n polynomial. So how to determine the degree n polynomial? We need n plus 1 equations. So here, we get n equations. And also we can, from the definition, here, the asymptotic behavior, the u to n, the leading order, the coefficients of the leader term is known, because from definition, it's, here's 1, and product, the asymptotic behavior, so the leading term, the coefficient of the leading term is 1. So then we have n plus 1 conditions. So this identities determines all the spectrum of the transfer matrix, because we just determine a spectrum of the polynomial, degree n polynomial. So we have n plus 1 conditions already, so we can get the spectrum. Okay, so what's the case of the homogeneous case? The homogeneous case, that means takes all these j's to be 0. Okay, then we get the homogeneous limit. But these identities, reduce to such an equation, just the difference. So we can get the derivatives, the nth order derivatives. We get the homogeneous limit. That's okay. Okay. Now, so because of these identities, we can assume so the transfer matrix acting eigenstate, the eigenvalue is lambda u, and so the lambda also satisfies these equations, because just from this, and then so we can determine the eigenvalue must satisfy such a equation. This is the actual term. So in some cases, the last term is 0, but for the systems without U1 symmetry, this term must be included. And here Q is the Q function, and Cu is the last term just determined by the asymptotic behavior when u tends to infinity. Okay, so why can we get such an expression? Okay, let's see. So for u takes the value of theta j. So from this, we can see d theta j is 0. So the last two terms are 0. So we get this expression. And then for u takes theta j minus eta. So here a is 0. So the first term and the last term is 0. We get this one. And then we take the product. Okay. This one times this one, we get this. Right? So that means lambda u is a solution of these identities. And finally, so because lambda u is a polynomial, the expression must be a polynomial 2. So we take all the residuals to be 0. That means the regularity, so we get the beta ansatz equations, and then we solve the problem. No matter the system possesses U1 or without U1, that's okay. That's universal. So we get this one. And finally, the regularity gives the beta ansatz equations. That's the procedure to solve the spectrum. Okay. Sorry. Yeah. Actually, we can use another expression to determine the spectrum. So we just introduce this one. So generalize the identities to a arbitrary u case. We should add such a term. But now we can see Tu is a degree n polynomial. Wu is also a degree n polynomial about the spectral parameter u, right? So now we have two n unknowns for the polynomials. But these equations are degree 2n equations. So we have 2n plus 1 coefficients. So this equation determines the roots of lambda u and w completely. Okay, this equation. So we can just assume the lambda u is a polynomial, so we can assume the zeros or the roots of lambda u is cj, w's roots is wj, so we can get different beta ansatz equations.
Why is it 2 and 3?
Sorry?
Position is on what? You choose 2 and 3?
Just from the definition. Yeah, Ru is 1, so trace we get 2. W is because when u tends to infinity, it must be 3.
Yes, and you don't mention that to fix this asymptotic, you have to fix the m also to be of the dimension of this.
No m at all.
But just before the slide, you say that you want to fix all the polynomial, and you have to.
Polynomial
is a function of degree n.
Degree n.
But it must
this is not a beta roots, just the roots of the transfer matrix, because the transfer matrix is degree n, so we have the.
I speak about the degree of q. Yeah, you should have, because you don't want.
Degree of q, that's okay. But so, yeah, from this equation, we could get all the solutions, including all the q's degree. So from 0 to n, no problem. But this equation, we just forget the beta roots, because for the transfer matrix is degree n, only n roots, right? And the W also, only n roots, right?
Sorry, could you explain? You have, in the two boxes, you have T with two different fonts. Are they the same T or they're different? So in the blue box, you have T with this sunny curly, and then in the red box, you have a different T. Is it the same T or different?
The same. But T theta j means U takes a special value.
Yes, of course, okay.
U is arbitrary.
Yes, okay.
Yeah, then U is arbitrary. Okay. Yeah, the second one is correct for arbitrary U, but the first one just for some special point at the inhomogeneous point.
About just the notation, because I think you have trigonometric for the first equation, and you choose the parameter eta to be 1.
And the T
yeah,
is the same. It was the
yes, sorry. Yeah, just one, sorry.
In the second equation, you can write also eta instead of 1. In the red box, you can write eta at the place of 1.
Yeah, eta is 1 here. I'm sorry.
No, I mean in the reverse. Can you substitute? It's more general. Than what
Eta is more general, just a crossing parameter, right? In the integral models, just the crossing parameter. But for the rational case, we just take eta to be 1. Sorry.
But this is renormalization of the U also for the Yangian.
Yeah,
x6.
that's okay.
Just shift.
Yeah.
Maybe not for x6.
Yeah. Here, you just understand. Eta is 1. Okay. So we get quite different Bethe equations. This now notice here. So we don't need any constraint for the boundary conditions. No matter it's periodic, with U1 symmetry or without U1 symmetry, that's okay. Yeah, just from the identity, we get the spectrum. Okay. Wow, it works. Good. And then from here, so we can calculate the physical properties with the roots of the transfer matrix rather than the roots of beta roots. Because here, we just take the logarithm of this equation, we get summation, but C to G just show some of the inhomogeneous parameters which we can take arbitrarily.
You have to keep them arbitrary
Yeah.
up to the end.
To the end, we take all this to be 0, we get the result. Just use the analytic properties to get finally we get the homogeneous limit. Okay, so here, so we can just define the roots of Z, the lambda U, to be rho Z. And we can also define the density of the inhomogeneous parameters, right? So, and then we can get a convolution integral equation. So with Fourier transformation, we get the spectrum of.
Can you recall which expression for lambda did you use? For going, the polynomial expression.
Yeah, yes. And then we take the logarithm, so we get the summation. And so then we can, so for n is large, we get continuum limit, so we can transfer this summation to be integral, and by defining two densities. One is Root's density and other is inhomogeneous density. But finally, after the calculation, finally we take sigma theta to be a Dirac function. So we get the homogeneous limit, right? Okay, good.
Z are the zeros of the transfer matrix, aren't they?
Sorry?
Z are the zeros of the transfer matrix.
Yes.
Yes.
Lambda are the
eigenvalue of the transfer matrix.
Okay, so yes, symmetry.
Right? So here theta just the auxiliary parameter, as the density is an auxiliary density, and finally we take this to be a Dirac function, so we get the homogeneous limit. Right? Yeah. Okay. So, now let's turn to the first example, how to quantize the particle, quantize a system in a topological space. Okay, so just like this is a Mobius stripe, and we can define the quantum space also in a Mobius-like space. And So the exact quantization procedure, of course, include the first one is what's the vacuum? Because there's no U1 symmetry. And even without a clear picture about the the particles. Yeah. Okay. So locally, at one point, if we define the inside is particle and outside indicates hole, then because here it just is a single phase manifold, so the particle and the hole are almost the same. So globally, it's the same. So we have no idea about a fermion in this space. So what's the vacuum or the ground state in such a system? And what kind of particles can exist in such a system? And so finally, so how do the particles alive in such a manifold? That means the dispersion relation. 5 minutes. This one? Oh, sorry. Okay, so just consider such a spin chain, but the boundary conditions changed with a knot in this. This is so-called anti-periodic boundary conditions, but it's in fact the topological boundary condition. And then this model has been studied by several authors. Okay, now here the monodromy matrix is defined just mostly like a Euro case, but with a twist, non-diagonal twist. And then, so the trace of the monodromy, the transfer matrix becomes B plus C, but not A plus D. So this is changed. That's why we call our method as off-diagonal beta ansatz. Yeah, this is start point. Okay, so but Hamiltonian, yeah, just as Euro. Now we can see the transfer matrices at the 0 point just is a shift operator, but twisted shift operator. But this one, the 2n is identity. So we can define, because this is also a shift operator, we can define the topological momentum. Just take this one. Yeah, it's this one, and the quantization of the K number is just when the number is half of that in the periodic case. Yeah, it's 2, and so this is a spectrum, the eigenvalue of the momentum. Yeah, so we get the topological momentum, the spectrum. Okay, there are also some other conserved charges, very special, just defined from the generator of the quantum group. Okay. Now, so we can use our method to define the eigenvalue of the transfer matrix, as is from these identities, we can get the spectrum. There's no problem, but here is no longer beta roots, but the roots of the transfer matrix. Okay. So, but of course, with the off-diagonal beta ansatz from the inhomogeneous TQ relation, we could get the beta ansatz equations with the this UG are beta normal beta roots, but with extra term. And then from these equations, we can get the patterns of the beta roots also possess the string patterns. But also we can get the roots of the transfer matrix from the beta roots. Yeah, just from this equation, yeah, from the TQ relation, here we let lambda u to be 0, and so from the TQ relation we get this, the Zj satisfy these equations. And from the patterns of the beta roots, we can get the pattern of the 0 roots. But the 0 roots are just only conjugate pairs in the complex plan, but without string structure. Because the string structure, the beta roots must be different from the 0 roots. And so these conjugate pairs only at the top and the bottom of the beta roots string. So we get only conjugate pairs, and from so the roots, the Z roots, just 3 kinds of 0 roots. One is real, the other is on the line of the half pi, and the others are all conjugate pairs, just symmetric to the real axis. Okay, so with these patterns, and now we can use the method I mentioned with the auxiliary inhomogeneous parameters. We can get this equation, and finally, we can change this summation to an integral equation, and after some Fourier transformation, we get solution of rho z plus. So, and of course, finally, we take the all theta j to be 0, or take the density of the theta to be delta function, and finally, we get this density of the roots. And so
this also in the thermodynamic limit. So the number of roots have gone to.
the number of roots is always n, because the polynomial is degree n. So we
Goes
have
to infinity, you take n goes to infinity to take the integral form. No, it's a number of sides. You have thermodynamical limit.
yes.
It's a question if they have n goes to infinity. It's your question, David?
Yes,
Yeah.
yes.
Yeah,
No,
I
since
think
it's
it's
considering
the case.
densities.
Yes, it's the case when you have the density. When you take the integral form, you take the density.
Yeah. Yes. Yes. So the roots of the transfer matrix is always n because of the degree n polynomial. But for the beta roots, you have different numbers for different solutions. But for the transfer matrix, the roots, the number of roots is always n, is fixed.
Sorry, this I don't understand, because this if you take the TQ equation, you see that the degree of Q must be that's different.
But the zeros.
Yeah, but at least you must have n beta roots. You can have more, but if you want to check, it was connected to my previous question, to fix the degree of Q,
Yeah.
when you take from your ansatz,
Yeah.
let's have a degree n, but when you want to satisfy the asymptotic, you say I need to have m equal to m. The degree of Q must be the same of degree of T.
Not really. Not really.
Or you have also
Yeah. You can. Yeah. The least, the minimum is n, but you can go arbitrarily.
for the others there are some kind you come to.
Yeah. Yes.
But the point is here you have the number of roots, beta roots grows at the same time of the number of roots of T.
But so the beta roots, you take different values of beta roots. Maybe you get the same solution physically, because you have an infinite number of Q functions. But the Hilbert space is fixed. Yeah.
If you ask the point, okay, let's take the minimal degree for the Q, you have only one, and the degree is n.
Yeah,
And
right.
for this one, you have, but it's not a big point. It's about, so the number is the same at minimal also. So, but the point is what you say, I'm curious, because you introduce the homogeneity, and at some point in the result, everything disappears. And it's what you say, that this delta function, the density goes to delta.
Yeah. So there is some trick, to take the inhomogeneous parameters just in a line, a straight line. So this is very convenient to get the integral. Yeah. Of course, you cannot choose the inhomogeneous parameter in the whole complex plane arbitrarily. Yeah, this just auxiliary parameters, right? So we can take our the most convenient way to do the calculation, right? Okay, so here are some kind of excitations. The first one is from the real here. The star is zeros. We take 1 from the real axis to the half pi line, so we get excitation. And we also can put the 2 roots from the real axis to the complex plane, get a conductor here. We get another solution, and also so arbitrarily high conductor pairs, we get all the excitation energies. So we can calculate these elementary excitations exactly in the, of course, in the thermodynamic limit. Okay, now let's so let me show you the most the simplest case. Just a free fermion we see topological boundary condition. This means, so at the end we have Cooper pair. Just turn the particle to be whole, whole to be particle, and connect this. This is the quantum Mobius stripe, right? So spin the particle hole, just twist at the end, and we have a ring. So this one. So even this a free fermion case, you cannot diagonalize it quite easily. So with our method, we can get, okay, the spectrum just on 2 lines, the quarter pi case. And in the ground state, all roots are on this line. And if we get an excitation from the lower line to the upper line, so we must keep the real part of the roots to be the same, not arbitrarily put on the upper line. So we take 1 here to the upper line, so this only can be here, and also the same. If we take 1 root to the upper line, so this same. This is topological constraint. So without any other solutions. So this means we have a particle and we have minus the offside momentum hole. But we know in a Mobius stripe, so the particle and hole are the same. So we have a pair excitation. What's this? This is Majorana fermion. Okay, because the particle hole are the same. And here we get it. So in such a free fermion system, but with topological boundary, a Z2 topological boundary, we get the Majorana fermion excitations. Okay. Yeah. Now, so we have the spectrum, but how to get the eigenstate? Because we cannot use the algebraic beta ansatz, because we have no obvious reference state. We have no obvious vacuum. So, but now we have the spectrum. Yeah, we know the eigenvalues of the matrix. So, of course, we can retrieve the eigenvectors from the known eigenvalues, right? And here, so the transfer matrix we know, but we can use the separation of variables to get orthogonal basis. But also, here we define these 2 sets of bases, the right side, right basis and left basis. These 2 sets of bases just eigenstate of du. This operator eigenvalue. Yeah, you can try. You see algebraic beta answers. Because unwanted terms at theta j is 0 automatically. So we get this is du's eigenvalue. Okay, so now we can define such a scalar product, just a definition. Okay, from here, so this is just a coefficients of the eigenstate. Now we input a transfer matrix in this scalar product. Yeah, acting this transfer matrix left, we get lambda, right? Because, right. So we get the eigenvalue is because psi is the eigenstate of t. But acting it to left, we have this one. So now we have the coefficients of the eigenstate in terms of basis. Okay, because lambda u is already known, so we get the coefficients, and so we can get such the eigenstate. But in the compact form, we just define the eigenstate to be d lambda j. Lambda j here are the beta roots, but acting on some unknown reference state. Omega is unknown. But so, yeah, here, so we can use this identity to prove that this state is indeed an eigenstate of the off-diagonal transfer matrix. But omega can be retrieved as this. In the homogeneous limit, we can get the omega is just the coherent, spin coherent state. It's very complicated. Okay, so yeah, for the open boundary, we have the same story. Okay, so yeah, I just stop my talk here. Just tell you a story how to define the spectrum, how to get the eigenstate, how to calculate the physical quantities with rather differently, analytically, without any even without any information of the states. Okay, that's all. So, thank you.
Any question?
Thank you for the nice talk. I would like to ask a general question about inhomogeneous TQ equation.
Yeah.
And that question is, this inhomogeneous piece, is this a purely quantum effect? So to be more specific, so if you imagine I have a classical XXX spin chain, then the classical analog of the Baxter TQ equation would be just the classical spectral curve equations, which would just be determined characteristic equation of classical monetary matrix.
Yeah, that depends, because the classical system usually is infinite dimensional.
Yes.
So it's quite different from the quantum case, because the local Hilbert space is, we consider just finite.
Yes.
But in the classical case, so it's quite special. Actually, there is no definition in the classical case with off-diagonal boundaries, because it's divergent. Yeah,
But also you would have the, say, determinant, a characteristic equation equal to 0, and really 0, no inhomogeneous piece. So do you only then see this inhomogeneous piece when you consider, say, highest weight representations or something like this?
Here, the homogeneous parameter just auxiliary. Yeah, we can need it in the statistical physics, in the vertex models. It's physically meaningful. But so for the quantum case, usually we can take this. But this is auxiliary tools to get to make the calculation quite simple. Otherwise, so you can you should do some derivatives, several orders. But this is simple, clear. It's analytic, so we can use this, and finally we take take the limit. Yeah.
The question? Okay, I have question, but maybe later. It's more technical about this this limit in integral equations. So, thank you, speaker again.
Yeah.